Alright, so welcome. Today we'll be talking about slope fields, and slope fields are really kind of cool. It's almost like dropping a pebble in the water and then seeing the ripples happen outward. But in this case, we're actually going to be looking at a function and then seeing how the slope is affected by using a differential equation. So it's almost like we're taking the differential equation, dropping it onto a coordinate plane, and then seeing the slopes of the tangential lines be produced from it. So what we're going to do first, here's the steps. Solve for the differential equation in terms of y prime or dy dx, however you like. If there is no y prime, solve for y and implicitly differentiate. Okay, and I should probably have a parentheses right there. There we go. Okay, have a table of values for x, y, and y prime or dy dx within the interval given. You might want to start at the origin and work out from there. Alright, now plug in those values into the table, solving for y prime or dy dx, and this will be your slope of your tangential line. So graph little sketches of them to make a slope field. Okay, and we'll start with an example. Okay, so x times y prime, so this is a differential equation because it has a variable in that's already been differentiated. Okay, minus y equals 2. So what we're going to do is solve for y prime. So xy prime is going to equal 2 plus y. Okay, and then we're going to divide both sides by that, and so we get y prime is equal to 2 plus x divided by y. Or, sorry, 2. Jeez Louise, screwed that up. 2 plus x, and I keep typing that. Holy shnikes. See, look at that. Keep doing it. Divide by x. Okay, there we go. I finally got it. Alright, so there's our differential equation. Okay, so what we're going to do next is make a table of values, and we're going to have 3 parts to it: the x portion, the y portion, and the z. Almost was thinking three-dimensional. The x portion, the y portion, and the derivative of y portion. Okay, so here's my table. It's a little bit messy, and I'm kind of going everywhere, but okay, the table of values within the interval given. So we didn't have a given interval, so we're just going to sketch our graph based upon just some initial facts. So if we just mark it out, this is sketching slope fields are always going to be your own interpretation. So don't feel like you have to have a positive answer for it just to be able to work with it. Okay. Right. Let me just sketch it. Okay. And plus you want to do whatever interval you want to do just to be able to work it out. Okay. So boom, boom. Ooh, that is a rough one right there. Let's get rid of that. Let's get rid of that one. There we go. Okay. Alright. Now this is one of the more easier processes because now you understand what differential equations are and how to get them. But what we're going to be doing is just sitting right here and just doing some calculations, okay? Alright, so, if we make x 0, this is going to be undefined. So these first two are just going to be undefined. Okay, and what type of slope that's going to be is that's going to be a straight up and down slope. So if we use a different color, actual graph, okay, so when we actually take a look at it, at 0, 0, that slope field will actually be going straight up and down, and at 0, 1, that slope field will actually be doing the same thing. So it's going to be two little lines looking like that. Okay? Alright, now if we plug in as x is 1 and y is 0, we're going to get a 2. Okay? Alright, so x is 1, 0, so that will look like that. So this slope is going to be 2. Okay, so the slope of that line is 2. Now if x is 1 and y is 1, then this should be 3. So this is going to be a little bit steeper than the last one, so this is 1, 1. Okay, so at 1, 1 it will be a little bit steeper. Oof, let me get rid of that. And I try to use the straight lines, try to use a straight edge when doing this because sketching is just a little bit harder. So this one's definitely going to be a little bit steeper. Okay. And you can move around as is. Alright, and I will. Okay, there we go. So it's a little bit steeper. Alright, now if x is -1 and y is 0, that's going to be a -2. Okay. Alright, and so once again, that is just the slope at that actual point. So -1 comma 0. So that is going to be -2. So it's going to be looking a lot like that. Okay, at -1 comma 1, that's going to be a -3, so that's going to be even steeper. Okay, I have a line. As you can see, it's kind of got like this siphoning effect. Okay. Alright, and that's going to be a -3. And the cool thing is you're just basically plugging in values and just working with it. Okay, now if I plug in a 1 for y, that's going to be 3 on top, -2, so this is going to be -3/2 right here. So that's going to be a little less steep than what it should be. So -2 comma 1 is going to be something looking like this. Okay, and 2 comma 0 is definitely going to turn into 1. Okay, alright, so that's a slope of 1. 2 comma 0 is over here. Okay, and as you can tell, this is a little bit less steeper than this point at 1 comma 0. Okay, and then 2 comma 1, 3 up top, so that's going to be 3/2, so that's a little bit steeper. Okay. Alright, and that should be at 2 comma 1, which is right here, so that should be just a little bit steeper, but not as steep as this one over here, which was a 3 right there. Okay, and as you sketch it more and more, you're able to see what's going on with the actual vectors. And these slope fields are actually pretty cool. So let me show you a completed picture. Okay, and this is courtesy of SOS Math, and it's the derivative of y equals 2 times x times y. Okay, and it starts out sketching it like this, and this is what it ends up with. And it's actually some pretty cool stuff that you can actually work with. Now, if you can imagine being a pitcher over on this side, and this is like a wind current, and you're throwing a ball over to this side, it would actually take a path like this. So if you threw up, it would go up, and then the wind would push it back down and go over here. And same thing here, up and down, up and down. And if you were to go straight across, because that's all the slopes that are really close to 0, okay, it would just go straight across. And that's some really cool stuff. Now here's one of y equals, or the derivative of y equals e to the -y. Here's what it actually looks like. So this is actually really kind of cool stuff when you're working with it right here. Okay, here's one of y prime equals 0.3 times y times 1 minus y over 15. Okay. Alright, this one's pretty cool how it's all set up. Okay. And as you can see, the slope field is a little bit more crazy as it goes. Okay, and then here's y prime equals y squared minus t. It would be something that looks like this. It looks a little bit more complicated, but in fact, it's actually just a parabola. Okay. So it's some really cool stuff when working with it. Okay, now here's a cool way of approximating an integral or the differential equation by using Euler's method. So number 1, write down the formula you're working with along with the initial values and what n is. Okay, so for example, I have my formula. The initial value y at 0 is 1, and n equals 4, and we're going to go to y equals 1. Okay, and we're going to use this formula. Y sub 1 equals y sub 0 plus the function as you plug in t sub 0 and y sub 0 times delta t. Okay, now we're going to make our tables beginning with t sub 0 all the way to y being t sub 0 and y sub 0. Okay, so we seriously have t0 equals t1 equals T2 equals T3 equals, okay, and we just keep going on, so on and so on. Alright, and we'll figure out where to stop from there. Okay, and then we're also going to have y equals, so y sub 0 equals, y sub 1 equals, y sub 2 equals, and y sub 3 equals as well. Okay. Alright, so we're going to find the initial values. So we already know that y at sub 0 is 1. Okay, so we already know that one right there. And t sub 0 is going to be the actual function in there, so that's going to start at 0 as well. Okay, and that's when we're plugging in 0 right there. So this is the t value right here. Okay, so now we're going to find delta t. Now delta t is going to be found by taking the initial value, so 1 minus 0, and then we're going to divide it by 4, and that's going to equal 0.25. Okay, so this right here is going to be 0.25, this is going to be 0.5, this is going to be 0.75, and then obviously we're going to go up to 1 because that's the ending point of what we want. So this should be t sub 4 equals. Okay, right, and so right there we should have probably a y sub 4. Okay, so now we're going to start plugging this up. What you're going to do is you're going to keep plugging in values until the values hardly change. Then you know you're done with an approximation, or at least in this case when we get to n equals 4. Okay, so here's how this is going to work. Okay, this is the formula we're going to be working with big time. Okay, so this is basically saying the new value is equal to the old y value plus the function when I plug in the old y and t values in, all right, times delta t. Okay, it's as simple as that. So the initial y value is going to be 1. Okay, and then I'm going to go plus. All right, now I'm going to plug in that value into here. So that's 3 minus 1, so that becomes 2. And that's going to be times by delta t, which is going to be 0.25. Okay? Alright, and what do I get? I get 1.5. Okay, because this turns into half, and half plus 1 is 1/2. Okay, now what I'm going to do is for the next value, I'm going to plug in that 1.5 in the beginning. Okay, and then I'm going to plug in the values of these two in here. So this is going to be 1.5 from 3, which is going to be 1.5, and then I'm going to times that by 0.25. Okay, and that is going to be, let me check my calculator real fast, 1.5 times 0.25. And that's going to be 0.375, so this is going to be 1.875 right there. Okay, and then that value I'm going to plug into here, 1.875 plus, okay, now I'm going to subtract 3, I'm going to subtract 1.875 from that, so 3 minus 1.875, and that's going to be 1.125. And that's going to be times by 0.25. And so this is going to turn into 2.15625. Okay, and that's when I get done doing work and all that stuff. And then I plug that in, so 2.15625, and I'm going to add that with, let's see, 3 minus 0.84375, okay, times by 0.25, okay, plus 2.1625, and this is going to equal 2.373 approximately. Okay, and as you can see, we keep getting approximately closer to the answer. All right, that is pretty much everything for this problem. I will talk to you guys later, and that's Euler's method and slope fields. Have a great day. Bye.